Okay, energy changes in reactions. We're studying in this chapter thermochemistry, the energy changes that occur during physical, chemical, and nuclear changes. So you might think of ice melting as an example of a physical change, really any change of state. Water decomposing, we're looking for a change in composition of the reactants and products. A new substance is formed. And then nuclear fusion or fission, which really gets the least of our focus, but that's an example of a nuclear change. So what force of attraction is being overcome when ice melts? Think about that. Capital E stands for energy. Can you fill in the blank? What is energy? The energy required to overcome? Hopefully you're thinking of intermolecular forces. Yes, in particular hydrogen bonding for water. But generally in physical changes, the energy is required to overcome intermolecular forces. Now, in a chemical change, what is the energy required to overcome? Hopefully you're thinking bonds. Oops. So the covalent bonds between hydrogen and oxygen atoms in the water molecule need to be broken in order for hydrogen gas and oxygen gas to form. I know you haven't studied nuclear changes in detail, but it's the force between the protons and the neutrons in the nucleus, those attractive forces that need to be overcome. And so in terms of relative magnitude of energy changes, which do you think experiences the lowest magnitude, lowest size of energy change? Physical, chemical, or nuclear? Hopefully you're thinking physical because those intermolecular forces are the weakest forces of attraction compared to the covalent or ionic bonds compared to the nuclear attractive forces within a nucleus. And so we generally see the range of energy changes for physical changes fall in an order of 10 to the 0 to 10 to the 2 kilojoules or 10 squared kilojoules per mole. So really from 1 to 100, somewhere in there, 1 to 10 to 10 to the 2. Okay, in the chemical changes, we'll see the range here be greater, so exponents of 2 to 4 here, so 10 to the 2 to 10 to the 4. And then we'll see greater than even 10 to the exponent 10 here for nuclear changes. So you can see that the magnitude of the energy change is increasing as we move from physical to chemical to nuclear changes. Yes, energy does have many different forms, and you can probably think of a campfire burning and think of the light energy, the sound energy, the thermal energy as you feel the transfer of that thermal energy. Perhaps you think of your cell phone and that it has a battery, so there's an electrical energy that is then converted to sound energy. What's happening inside that battery, or let's say in the gasoline engine of a car, will have a chemical potential energy. Same idea with your food. You eat your food and get energy from your food. That's chemical potential energy from the food. So there's other kinds also, but those are some examples of the different forms of energy. Now, the first law of thermodynamics, or this study of energy changes, is that energy is neither created nor destroyed. So energy will just change form as opposed to be lost or created. So here's some examples. You eat your breakfast and then you walk to school. So what form of energy is the energy in when you're eating the food that is your breakfast? Well, it's the energy stored in the molecules of your breakfast food. And so we call that chemical potential energy. And when you walk to school, now you've transferred that into energy of motion, mechanical energy, kinetic energy. We think of the sun, right? The sun you might think of as solar energy. And that's being transferred to green plants as they undergo photosynthesis. So in fact, the plants take the sun's energy and convert it to chemical potential energy, stored in the glucose molecules that are produced in photosynthesis, or the majority of which are stored in the glucose molecules. A fuel, a gasoline in your car, is an example of a chemical potential energy. So we have molecules of the fuel, and that energy gets transferred into the mechanical energy or kinetic energy of the car as it's moving. You might also think of thermal energy as the car parts heat up. Okay, so all forms of energy can be classified as either potential or kinetic. So when you think of potential energy, think of that being due to position or composition. And we'll look at that with respect to molecules in a minute. Whereas kinetic energy, this is due to motion. So if we're going to focus in then on the concepts of energy as it applies to molecules, then first we look at potential energy. And again, think position or composition. So what are we talking about? Position of what? Composition of what? Well, the position of the nuclei and the electrons in the atoms that make up the molecules. And composition, right? The types of atoms. Is it carbon? Is it oxygen? Is nitrogen present? Is there hydrogen? You know, the composition, the makeup of that molecule. And you can see here an example of CO2, that in that CO2 molecule we have two carbon double bonded oxygen bonds. So C double bonded O occurs twice here. And there's 799 kilojoules of energy per mole of C double bond O bonds. And so that's an energy that's being stored in the bonds of the CO2 molecule. Now, kinetic energy, as we remember, is due to motion. Kinetic energy of molecules, we need to think of how are the molecules moving. So you may recall from grade 11 the vibrational, rotational, and translational motion of molecules. That's what gives particles their kinetic energy. Now, a few other terms come into play here. What is temperature really measuring? Well, the average kinetic energy of the molecules. So when you hear temperature, think of kinetic energy. So particles are moving, and at a higher temperature, they're moving faster. But temperature is the average. It's a measure of the average kinetic energy of all the particles. So some will be moving slower and some faster than others. Temperature is giving you a measure of the average energy of motion of the particles. Thermal energy, on the other hand, think total or sum. We're looking for the total internal energy of the sample, which really is a sum of the potential and kinetic energies of all the particles. So it's true here that as the particles move faster, as you increase the speed, that will increase the kinetic energy, which has then increased the thermal energy. But even more significantly, think about if you have more of a substance. If you have more substance, then you're increasing the total energy of that sample. And so that will increase the thermal energy. So as I've indicated here in red, for temperature, think average. For thermal, think total. All right, so if we compare, and you can practice your understanding of this by thinking of a glacier and a cup of tea. So we think of a large glacier up in the Arctic. Okay, so we have this huge, huge mass of ice. What would you expect to be the temperature, low or high there? And certainly as compared to the cup of tea. Hopefully you're thinking that the temperature here is low, which really means that the average kinetic energy of the particles is low. So on average, those particles have a lower average kinetic energy than the cup of tea. Now, what about thermal energy? Thermal energy is the sum of all the potential and kinetic energies of all of the particles in the sample. So even though that cup of tea has a much higher temperature, a higher average kinetic energy, of the particles. Think about the sheer billions and billions more of particles there will be in that glacier compared to the cup of tea. And so having a significantly greater amount of substance means that this glacier is going to have a higher thermal energy than the cup of tea. So as compared to one another, the glacier has the higher thermal energy. Not because its kinetic energy on average is higher, but because there are many more particles in this glacier than there are in the cup of tea. And so the sum, think total, it's going to have a higher total than the cup of tea. All right, so we've been just talking about thermal energy there. So what does it mean when thermal energy is transferred, or what terminology do we use there? We use the term heat. So that's misused in the scientific context, so I'd just like you to be aware that heat is actually a verb. So to heat a pot of water means to transfer thermal energy from the stovetop, the element or whatever it is, the blue flame of the gas stovetop or the electric element. So we're transferring thermal energy from the stovetop to the water. So when we say an object is heated, we're talking about thermal energy being transferred from the hotter substance to the colder one. Okay, there's a few other key terms in this lesson here. System and surroundings. Okay, so you're going to hear me refer to that a lot. We'll be studying different chemical systems. So what is a system? Well, it's all the reactants and products. So when you write a chemical equation, it's going to be everything that's written in that chemical equation. Systems can either be open, closed, or isolated. The idea of an open system, an example being a campfire, you have the wood burning, and the gases that are being produced during that are able to vent into the open air, into the atmosphere. So matter freely leaves the system. Does energy leave the system? Sure, you can huddle around that campfire and warm your hands or cook food over it. And so the campfire burning, that combustion, those combustion reactants and products are the system, but they definitely are allowed to leave the system because of the setup of the campfire in the open air. So an open system exchanges matter and energy with its surroundings. A closed system exchanges only energy. So imagine you've injured yourself, you grab a cold pack, so a plastic bag that is sealed, you mix the contents by squeezing this package, and suddenly the package starts to feel cold. And you put that on your injured joint, and the energy, the thermal energy from your knee, for example, transfers into the cold pack, the colder object, and that helps relieve the swelling in your injured knee. So matter is not being exchanged between your knee and the cold pack, but energy is, transfer of thermal energy. And so that's an example of a closed system. An isolated system would be where neither matter or energy are exchanged with the surroundings, and really that's impossible to truly create a true isolated system on Earth. But our goal will be, as we study energy changes, to isolate systems as best we can, and we'll talk about that more in the next lesson. I've mentioned the surroundings here. What do I mean by the surroundings? Just any matter that is around the system. So in the campfire example, it would be the air around and the person standing there, or the marshmallow that you've got on a stick over the campfire. In the cold pack example, the air immediately surrounding the cold pack, your hand if you're holding that cold pack, your knee if that's the injured joint and that's where you're resting the cold pack. Those are examples of the surroundings. Okay. Moving on, it will be helpful to think about this diagram right here. So having the system inside a circle and the surroundings. And we're going to be imagining situations then where energy will overall leave the system. And we will also have situations where energy as a net change is going to be entering the system. So we'll see both types of reactions. Okay, so endothermic and exothermic reactions. This is the last component of the video. Here we're looking at, in the first equation, an oxygen gas molecule. So imagine that those two oxygen atoms are bonded together. And on the right side, we see free oxygen atoms. So in fact, the double bond between the two oxygens has actually been broken in order to form two separate oxygen atoms. So definitely we know that from our study of covalent bonding that O2 molecule is more stable than the free oxygen atoms. The octet of each atom is satisfied. In chemistry, when a molecule is more stable, it has lower potential energy. Those free oxygen atoms are definitely less stable, and they have higher potential energy. So if you just look at how I represented that in the quick sketch on the right here, think of this down here as the origin, and so the potential energy numbers are increasing as you move up the y-axis. So if you look at where I drew the line for the O2 molecule, I've drawn it down here, which is a lower value than where I drew the potential energy of the products. So the idea is that this is a lower potential energy here, and this one up here, right? This is a higher. So can you see how this is just a pictorial representation of the reaction on the left in terms of the change in potential energy? Now in the second reaction, or second equation, I've shown a different reaction. We have a free oxygen atom and an oxygen molecule coming together to form ozone. Now I won't get into the structure there of the ozone, but I'll just put the three oxygen atoms together. And so that free oxygen, never stable on its own, we're forming O3. So we have definitely less stable reactants here because of that free oxygen compared to having the O3 molecule formed. And so this is our more stable side of this equation. And so if we transfer that then to make the connection to potential energy, more stable is lower in potential energy, and less stable is higher in potential energy. And so we see the reactants here showing up at a higher potential energy compared to the products. All right, so what we're essentially showing in the first equation is that in order for the O2 molecule to form those products, energy actually has to be absorbed. So I'm going to come back here and add in an energy term in order to form those higher potential energy products. In the case of the second reaction here, in the formation of the O3 molecule, the ozone, we can see that the reactants have a higher potential energy, and as that drops and lowers in the products, energy will be released. And so we refer to, as you see in the title here, endo and exothermic, we refer to these reactions as endothermic when the energy term is on the left side of the arrow, on the reactant side, and we refer to the reactions as exothermic when the energy term is on the right. And so that's an important summary or statement to make for yourself, that the reactants plus energy will form products. That's the idea of an endothermic thermochemical equation, and an exothermic chemical equation will have the reactants form products releasing energy. So very important to take note of that. Okay, last part of this lesson here is just to look specifically at an example of a reaction that doesn't involve free atoms on either side. So it's a little bit harder to predict what's going on here. So we'll look at this reaction in a number of different ways through our unit, but just to draw on information you have already, we can think of this methane molecule as being a carbon singly bonded to 4 hydrogens. Then we have 2 oxygen oxygen molecules, which we know experience a double bond between the oxygen atoms. We have a CO2 molecule, and then we have 2 water molecules. Okay, just completing these structures here. And so the idea is that on this side of the reaction, energy is required to break these bonds. Absolutely. If we're going to form new products, we're going to have to break bonds in these reactant particles. That is always true. Energy is always required to break bonds. On the right side, new bonds are being formed. Well, energy is always released when new bonds are formed, which you can go back up to our ozone example and see that energy is being released when the ozone molecule is being formed. And our first example showed that energy was required to break the O2 molecule up into free oxygen atoms. So ultimately now, when you look at a more complex reaction like this, the question becomes, which energy is greater here? Is the energy on this side required to break bonds? Is that a greater value than the energy that's released? If it is, then we'll have a net change where energy is required overall absorbed in the reaction. If we have an example where the energy that's released is greater, then we'll find that overall the energy is released from the system in that situation. And so if I were to just peg, like totally made up numbers just to help you understand this concept, let's say that 1,000 kilojoules of energy is required to break the bonds in those molecules. And on the right side, let's say that 1,500 kilojoules of energy is released. So if 1,000 kilojoules is needed to break bonds and 1,500 kilojoules is going to be released, then we're essentially going to have, I'll say negative 500 kilojoules here, the negative really indicating that 500 kilojoules of energy is released overall. And so what we've just determined here is that we've just shown that when energy is being released overall here, that's considered an exothermic reaction. Because remember the form that we just wrote, that when reactants convert to products and energy is being released, energy is on the product side, then it's an exothermic reaction. So in another example, if you had 2 reactants and 2 products here, and let's say that in this example, 800 kilojoules was needed on the left side to break bonds, and 600 kilojoules was needed on the right side in order to, or was released, when new bonds were formed, then if we look at the difference here, we'll see that we have a greater number, we're getting a positive difference here in energy. And in fact, that means that positive we interpret as 200 kilojoules is absorbed overall. So energy is always being released when new bonds are formed. There's 600 kilojoules of energy being released when the new bonds are formed. However, because 800 was required to break the bonds, it turns out the net or overall change is 200 kilojoules of energy being absorbed. And when energy is absorbed overall, that is our endothermic reaction. And so we would end up writing this as A plus B plus energy forming C plus D. Whereas in the combustion reaction, we would have put the energy on the right-hand side like we saw right here. Okay, that's it.